Hey guys, welcome back from Easter break. I hope you had a restful and relaxing time, and I hope you had a very nice Easter. We are starting our last chapter today. It is on what are called conic sections. So just a quick definition of what that means. A conic section is the different shapes that you can get by intersecting a double-naped cone, which is just two cones attached at their vertices. So you see in the picture here that there are four different things we're looking at. If we just go straight across, you get a circle. If you go at a slant, you get what's called an ellipse. If you go at a slant that just intersects one of them, you get what's called a parabola, which we've talked about those before. We're going to look at a new formula for that this chapter. And then if we went straight up and down, we get these two shapes, which is called a hyperbola. So that's what a conic section is. We're going to spend this first week easing our way into ellipses. So that's what our focus is going to be for the rest of this week. And then we're going to talk about parabolas and hyperbolas the following week. So looking at a conic section, it's going to have some form of this equation here. Different things will be missing, which is what's going to control what the different shapes are, or different negative signs are going to be in different places, but it should be in that kind of form. Something with x squareds and y squareds and x's and y's. And then each conic section can be defined as a locus or collection of points satisfying a geometric property. For instance, a circle is a set of all points equidistant from a fixed point. So that's what you're going to see on the next page as a demonstration about an ellipse. So had we been in class, I would have done this on the board for you guys. I would have put two magnets down and then used a string to do this. Watch what happens. So just those two toothpicks and a piece of string makes a perfect ellipse. And that happens because of the definition, which we're going to see on the next page. So the definition of an ellipse is a set of points in a plane, the sum of whose distances, that's represented by the string, from two distinct points called the foci, that was represented by the toothpicks, is constant. So that string stays the same all the way around, and it stays the same total distance away from the foci points, which is what makes the ellipse. So let's talk about some terms we're going to see. I'm actually going to go a little bit out of order. Let's talk about the major axis first. The major axis is the longer of the axes. So if it's vertical, it has a vertical major axis. If it's a horizontal ellipse, it has a horizontal major axis. So that's where your major axis is. The center then is the point that's smack dab in the middle there. The vertices are the points on the edge. So these are vertices here. And then the minor axis is going to go the other direction, and it'll be perpendicular to the major axis. That's the minor axis, that's the minor axis. And lastly, the foci would be somewhere in here. They always lie on the major axis, always in the same direction as those vertices. So that's a focus point, and that's a focus point. They should always be inside the ellipse. So then we're going to look at what makes the ellipse go in different directions based on the equation. So remember, I always talk about what's in control. This up here is your rule about what's in control. A squared will always be the larger number. The larger number is what's going to tell you what's in control. Whatever variable has the larger number, that tells you what's in control. So if you look at the first equation, a squared, which would be the larger number, is under the x squared, which is why this is going horizontal, because x is in control. And the second equation, the a squared, is with y, which makes it go vertical because y is in control. Okay? Then we have all sorts of information here The major axis is 2 times a, the minor axis is 2 times b, but to get both of those you do have to take the square root of the bottom. And then this is going to be a super important formula down here that we're going to use to help us to find the foci. The foci will always be the c distance away from the center, and you can get the c by doing a squared minus b squared. So here is our saying that we're going to say to help us graph these. We start at the center, and then we move the square root of the denominator in the direction of the numerator. If you take the square root of the bottom and move the direction of what the top letter says, that's how you can graph these. So let's start by graphing. If you look at this, the first thing that just pops out at me is the bigger number is here. So that tells me that in this problem, x is in control. And then we can look at each fraction to help us decide where to go. If I take the square root of 36, that's going to be moving left and right because that's where the x is. So that means we're going to go left and right 6. The center for all of these, the start for today, is going to be 0, 0. So we're going to go left 6 from the center, and we're going to go right 6 from the center. And then the next fraction has a y in it, so if I take the square root of 9, we get 3. That tells me, since it's y on top, square root of the denominator in the direction of the numerator, that we're going to go up and down 3. So I'm going to go up 3, put a dot, down 3, put a dot, and then I can graph my ellipse around those points. The last thing we have to be able to do is find the foci. We have to use the formula to do that. So to find the foci, the formula looks a little familiar. It's c squared equals a squared minus b squared. It almost looks like Pythagorean theorem, but is not quite. So it's c squared is equal to, a is always the bigger one, so it's going to be 36 minus 9. Remember, those are already squared on the bottom, so you can just plug them directly in. You get c squared equals 27. And then take the square root, you get c is equal to 3 radical 3. Then to decide how to write the coordinates, you have to remember what was in control. Since x was in control, that's going to control the x part of your coordinate, so it's going to go to the right, radical 3 over 3, and then it's also going to go to the left, radical 3 over 3, comma 0. That's where your foci will end up. To help you graph them, you can type that in your calculator. That's 5.2, so that tells me that I'm going to go over just past 5 and put it down, and then just past 5 and put it down. They should always end up on the major axis and inside of the ellipse. Let's try another one. So in this next one, first thing that pops out at me, I'm thinking about what's in control. This is where the bigger number is. The bigger number for an ellipse tells me what's in control, so I know y is in control. And then I'm starting at 0, 0. And I'm going to move in the direction, square root of the denominator, in the direction of the numerator. So square root of 25 is 5, and because that has an x on top, that means I'm going left and right 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then if I take the square root of 49, that's 7. That has y on the top of it, so that tells me I'm going up and down 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then I can draw my ellipse. I try and usually draw half of it. I kind of didn't say that on the last one, but I try half of it on one side, and then I go on the other side and draw the other half. I can't do it in one big swoop. It doesn't work very well. So that should be your ellipse. Much better at doing this at Notability. There, that's better. And then we have to find the coordinates for the foci. Again, it's just a formula. It's c squared equals a squared minus b squared. Always make sure you're putting the bigger number first as a squared. So it's going to be 49 minus 25. We get c squared is equal to 24. And take the square root. So then c is going to equal 2 radical 6. This time y is in control. So that's going to end up in the y coordinate. It's going to be 0, comma 2 radical 6 as one foci. And the other one is 0, comma negative 2 radical 6. And again, to help you graph it, if you want to put that into your calculator, that is approximately 4.9. So I can go over 0, up 4.9, and over 0 down 4.9. And if you notice, those are on the major axis, the longer one, and they are inside of the ellipse. So this next one, we don't have any fractions, which means we are not allowed to graph it yet. In order to graph them, they need to equal 1 first. So the fact that this doesn't say 1 here, you need to remember that it needs to equal 1 for you to be able to graph it. So your first step here is actually to divide by 144 so we can get that side to be 1. And we can see what these fractions are so we can figure out what's moving where. So then that ends up being x squared over 9 plus y squared over 16 equal to 1. And then we can do the same rules. Square root of the denominator is 9. Move in the direction of the numerator, so that means I'm going left, right, 3. So starting at the origin, left 3, right 3. And then square root of the denominator is 16. We get 4. Direction of the numerator, y is in the numerator. So that's going to be up and down 4. 4. And then we can draw our ellipse through there. Try and make it look curvy, not like a football shape so much, but curvy on the ends. And then to find the foci, the formula is c squared equals a squared minus b squared. And this time we get 16 and 9. We get c squared equals 7. And take the square root, so we know c is 7. And based on what's in control right now, which I hadn't talked about yet, that's what determines where that radical 7 is going to go. It's the one that had the bigger number. So y was in control. It also is going vertically, the ellipse, so I know that those have to go in the y position. So it's going to be 0, comma, radical 7, and 0, comma, negative radical 7. And radical 7 is about 2.6. So that's going to be right in here, and that's going to be right in here. Again, on the major axis and inside of the ellipse. And that is all for today. So you have a problem to try on ClassKick just so I can see how you guys are doing with this. And then you have just a few homework problems to try just to make sure you've got a good handle on what's going on with these ellipses. All right, have a good rest of your day.